Video we will use LINEST and SERIESSUM to generate the ERF function, the data set of the ERF function, and apply regression, the best fit regression. So here we have an ERF function which returns the integral of the Gauss Error function over an interval of values. So we generate the function over the values of -2 to +2 over x. So this is equal to RA formula, ERF of the x values. And we will regress this to the best fit. Generate the chart and choose the best trend line that can fit. The linear will not work. Let's try moving average. It won't work because the points are outside the line. Power series, still it will not work. It works only on the positive values. The logarithm also works only on the positive values of x. We'll try exponential. All the points are outside the line. We'll try polynomial. But we can make this better because this is the second degree. We'll work on the third degree. Now the points are close to the line. And our r squared is point, the goodness of fit is 0.997. Let's try to the fourth degree. We still get the same goodness of fit. So we'll just go back to the third degree. The lines are still in, or the points are very close to the line. So it is the polynomial regression to this third degree. We'll calculate the values of the coefficients using LINEST. So our coefficients are B0, which is 0. Our B1 is 0.945. Our B2 is 0. Our B3 is -0.116. We'll calculate these values using LINEST. To do that, we have to complete the x squared and x cubed column because we are using the third degree. So we start with the x column, RA formula of the x values raised to the power 1. And the x squared column will be RA formula of the x values raised to the power 2. And the x cubed column will be RA formula of the x values raised to the power 3. Now we can enter the LINEST. You can use the LINEST for this. Data y and data x. So our B0 is 0. Our B1 is 0.94485, rounded up as 0.945. Our B2 is 0. Our B3 is -0.115889, rounded up as -0.116. We'll also generate the expansion of this function, of the Taylor series expansion, or Maclaurin series. So we have an expansion formula. It's 2 over pi times the quantity z minus z cubed over 3 plus z to the 5th over 10 plus z to the 7th over 42, that's minus, plus z to the 9th over 216 until -1 to the power n times z to the 2n plus 1 all over n squared plus 2n plus 1. We'll begin with the denominator. So starting with the values of n, 0, 1 to infinity. In this case, we cannot reach infinity. We'll just work on the limits of our data set. That's 10. We'll start with the denominator, which is our right formula. 1 over the factorial of the n values. So we have worked on the factorial. Then the 2n plus 1. So we have to multiply that with 2n plus 1. Two times n plus 1. Okay. Next, the numerator, negative 1 to the power n. So that's negative 1 to the power n. So we have minus 1 to the power n. So we're good. So the third degree is 0.1 and the seventh is negative 0.023. Now we can enter the expansion, which is RA formula. We have 2 over square root of pi, so 2 times square root of pi times series sum of the x values raised to the power. So raised to the power 1, 3, 5, 7, 9. So that's raised to the power 1 starting with 1 and the interval is 2. And the coefficient will be this range. Something went wrong here. Oh, this is the pi. But there's something wrong here. That's 2 over square root of pi. So that's 2 over square root of pi times the series sum. So our values are very close. The expansion is almost the same as the function itself. We'll insert this to the chart. And insert the trend line as well. Use the same format. Polynomial raised to the power 3. We'll show the equation on our square as label. So we have the trend line. So ERFX equals 0 plus 0.943, which is almost the same as 0.945, plus 0 minus 0.114, almost the same as 0.11, negative 0.116 or negative 0.114. And we will regress, we will enter the LINEST for this. So LINEST of data y and data x. So our B0 is 0. Our B1 is 0.942575 rounded up as 0.943. Our B0 is also 0. Our B3 is negative 0.11446 rounded up as negative 0.114. This completes the polynomial regression of the error function and its Taylor Maclaurin series expansion.